I've been into physics for basically my whole life, and I figured, okay, I've got the basics covered. But it turns out I was completely wrong about one of the most fundamental things there is, and I'm willing to bet you are too. It's all about how something gets from point A to point B. So let's just tear that whole idea apart, shall we? And uncover what might be nature's most convincing illusion. All right, so let's get right into it. For the longest time, I just assumed, well, what everyone assumes, right? That every object has one and only one path through space. You throw a ball, it makes a nice, clean arc. A laser pointer, a straight line. Super simple. But what if I told you that's not what's happening at all? What if that ball, that beam of light, is actually trying out every single possible path at the exact same time? And that single line we see is just an illusion, a ghost made up of a zillion other possibilities. I know, it sounds completely nuts, but that's what we're here to show you is actually true.
So, where do you even start with something that seems so obvious? Well, it all begins with a little puzzle. A puzzle that nature, for some reason, seems to solve without even thinking about it. The mystery of the fastest path.
Okay, picture this. You're a lifeguard. You see someone struggling in the water. What's the absolute fastest way to get to them? Your first instinct might be a straight line, but that's a trap, right? Because you can run way faster on the sand than you can swim in the water. But if you run too far down the beach to make your swim shorter, the whole trip takes too long. The actual fastest route is this clever mix of running and swimming. Now, we can sit down and figure that out with a little math. But here's the crazy part. A simple beam of light does this instantly, automatically, every single time it goes from air to water. It bends just enough to take the fastest possible route. And that just begs the question, doesn't it? How in the world does light know what to do? It doesn't have a tiny little brain or a map. It's like it somehow sees the start point and the end point, does a quick calculation, and picks the best path before it even leaves. For a long time, I just figured, it's just following some simple rule at every point, and it's just a cool coincidence that it ends up being the fastest. But nope, that's not it. The real answer is so much weirder and honestly so much cooler. The truth is wrapped up in this really profound law of the universe called the principle of least action. And it basically says that everything in nature, and I mean everything, from a photon of light to a planet zipping around the sun, always picks the path of, well, the least effort. It minimizes this thing called action. You can think of action as kind of the total cost of a journey when you balance out the energy used and the time it takes. For hundreds of years, physicists just saw this as a clever shortcut, a neat math trick. But then, right at the start of the 20th century, they realized, oh no, this isn't a trick. This is everything. And where did this huge revelation come from? Believe it or not, it started with a really down-to-earth problem over in Germany. They were trying to build better light bulbs. Seriously. They just wanted to know how to make a hot piece of metal glow with the most light possible. But none of their physics could explain how it worked. That one simple, practical question, it set off a bomb in the world of physics. Over the next 20 years or so, our entire picture of reality just got turned upside down. You had Max Planck in 1900 saying energy comes in little chunks, then Einstein comes along with a photon, then Niels Bohr figures out the atom, and then de Broglie says, hey, maybe particles are actually waves. Everything we thought we knew just shattered. And it all began because the old physics just completely and utterly failed. And when I say it failed, I mean it failed in the most dramatic way possible. The existing theories, what we now call classical physics, predicted that any hot object, like that light bulb filament, should be blasting out an infinite amount of energy, especially in the ultraviolet part of the spectrum. Which is just ridiculous. You can't get infinite energy out of a light bulb. They even gave it this awesome name, the ultraviolet catastrophe. It was the ultimate proof that the old ideas were just dead wrong. So the guy who cracked the code was Max Planck, and he tried everything, he really did. Finally, in what he himself called an act of desperation, he just decided to break one of the biggest rules in physics. He said, what if energy isn't a smooth, continuous flow? What if it only comes in these little, bite-sized packets? He called them quanta. He thought he was just fudging the math to get the right answer, just a little trick. But the thing is, it worked. It worked perfectly. You've probably seen his famous equation, E equals hf. It just says the energy of one of these packets depends on its frequency. But the really mind-blowing part is that little letter h, Planck's constant. When Planck worked out what its units were, he must have been stunned. It wasn't a unit of energy or time or anything like that. It had the units of action. He had accidentally discovered the smallest possible piece of action in the entire universe. And just like that, action went from being a clever math trick to being the fundamental grain of reality itself. Well, Planck's idea just blew the doors wide open. If energy comes in chunks, what else does? People started asking questions. And the next big leap, man, it was so out there, it completely changed what it even means to be an object. So, flash forward to 1924. There's this young student, Louis de Broglie, working on his PhD, and he has this wild thought. He thinks, okay, we know light waves can sometimes act like particles, so what if it works the other way around? What if particles, like electrons, can act like waves? He proposed that literally everything has a wavelength. And this idea suddenly solved a massive mystery about atoms, why electrons can only be in certain specific orbits. If an electron is a wave, then for it to be stable, it has to fit a whole number of its wavelengths perfectly around the nucleus. Kind of like how a guitar string only makes a clear note when it vibrates in a clean pattern. All of a sudden, this arbitrary rule had a real physical explanation. And here's the absolute key takeaway from that. If an electron is a wave, it's not a little dot anymore. It's smeared out, it's diffuse, and think about it. If something is smeared out, how can it have a single, precise path through space? The answer is, it can't. The whole idea of a single trajectory just starts to fall apart. But it wasn't until the brilliant and eccentric Richard Feynman came along that someone took this weave idea and pushed it to its absolute brain-melting limit. And in doing so, he finally figured out how light knows which path to take. As the legend goes, Feynman was thinking about that classic physics experiment, the double slit, where a single particle acts like it goes through two holes at the same time. But Feynman just kept pushing that idea. He said, okay, what if we add a third slit? The particle has to consider going through that one too. What about a fourth, a fifth? What if we just keep adding slits until there's no wall left at all? What if there's no screen either? When you follow that logic all the way, the conclusion is just unavoidable. To get from point A to point B, a particle doesn't just take one path. It takes every single possible path. And I don't just mean the straight one. I mean the path that loops around Jupiter first, the one that wiggles back and forth a million times. Every single path. Okay, so if it's taking all these bazillion paths, why on earth do we only ever see one? This was Feynman's stroke of genius. He realized that most of them just cancel each other out. Think of every possible path as having a little arrow associated with it. For all the truly bizarre paths, the ones that go all over the place, those little arrows are all pointing in completely random directions. When you add them all up, they just fizzle out to nothing. It's called destructive interference. But for the paths that are really, really close to that classical least action path, all their little arrows line up almost perfectly. They add together, they reinforce each other, and they create the one strong, visible path that we actually observe. That's constructive interference. So that nice, clean trajectory we see every day, it isn't the real path. It's not the only path. It's really just the average. It's the consensus that emerges from an infinite number of quantum possibilities where almost all of the crazy outliers have canceled each other into oblivion. That single path we thought was so real, it's an illusion. A beautiful illusion, but an illusion nonetheless, born from overwhelming probability. Okay, I know what you're probably thinking right now. This is a cool story, but come on. Is there any actual proof? Can we really peek behind the curtain and see any of these other so-called impossible paths? And the amazing answer is yes. Yes, we can. Check this out. There's a brilliant experiment that proves this. Step 1, you shine a light on a mirror. And just like you learned in school, you see one bright reflection, right where it's supposed to be, the path of least action. But then you do something really sneaky. You use a special material to cover up only that one correct spot on the mirror. Now, logic says the reflection should just vanish, right? But it doesn't. What happens instead is you suddenly see new, dimmer reflections popping up in all these other impossible spots on the mirror. So what is going on here? Well, by blocking that main, super efficient path, you've stopped the constructive interference that was drowning everything else out. It's kind of like if you silence the loudest person in a crowded room, all of a sudden, you can hear all the other conversations that were happening all along. Those faint, impossible reflections, that is direct physical proof that light was always taking those other paths. They were real the whole time, just hidden. And listen, this isn't just some quirky little thought experiment. This is absolutely fundamental. The principle of least action, seen through this Feynman sum-over-all paths idea, that is modern physics. It's the language we use to describe everything from light and magnetism to how quarks and gluons behave. Seriously, no one doing particle physics today thinks about it any other way.
Which brings us really to the biggest quest in all of science. When you hear about physicists searching for a theory of everything, they aren't just looking for some big, complicated equation. What they're really hunting for is the master action, the one simple, elegant rule that governs action itself. The rule from which everything else in the universe, gravity, quantum mechanics, the whole shebang, just naturally emerges as the path of least resistance. Finding that, well, that's the holy grail.
Health is the most precious gift. If this video helped you or someone you love, please like, subscribe, and share so more families can stay safe and healthy.